Mahanta, Assistant Professor GSS Department of Physics, for this Friday faculty seminar. I'm very glad because Debasish and me share the same Gurukul, Desenpost Nasan Center for Basic Sciences. So I have a great respect to him also. So in short, Debasish Das Mahanta has completed his PhD from Desenpost Center, Kolkata. Then he completed his 4 years postdoctoral program from Ruhr University, Bochum, Germany. And then he flew to UT Austin, US. And then he came to GITAM and joined as an assistant professor in Department of Physics. His research interest is aligned with the investigation of the role of the intermolecular interaction in various biomolecular phenomena by using spectroscopic light matter interaction and MD simulation techniques. He generally uses FTIR spectroscopy and MD simulation to study the liquid material. So Debasish, floor is yours.
Thank you very much, Krishna. All for joining in this talk. So this is an informal meeting. Please stop me anywhere and feel free to discuss. So yeah, the title of my talk is Dance of Molecule. So whenever you are dancing, you need to have some music. Otherwise, there should be something which we follow whenever we are dancing. So what the molecules are following in this case? So actually the hydrogen bond, or in broader sense the intermolecular interactions, are the music here. And due to that intermolecular interactions, it may be hydrogen bond interaction, it may be van der Waals interaction, it may be electrostatic interaction also. Whatever may be the interactions in between the two molecules, that is the playing the main governing role. And my full investigation, my full research is aligned to this topic, that investigating the role of the intermolecular interactions in various biophysical properties or phenomena. I am Debasish Das Mahanta from Department of Physics. Regarding my academic journey, I have completed my PhD degree, doctoral degree from Desenpost National Center for Basic Science. It is in Kolkata, under the supervision of Professor Rajiv Kumar Mitra. Then after that I moved to Germany, Ruhr University, Bochum, where I have worked with Professor Martina Habinet. After joining GITAM, I found that Professor Patil sir is here. So he was also there in the same university, Ruhr University, Bochum. Maybe our time is not same, so I never know. Okay, after that I moved to UT Austin, University of Texas at Austin, where I have worked with Professor Carlos Weiss. So during my PhD time, I worked on various aspects of spectroscopic technique, that is the light matter interaction, and the molecular dynamic simulation, a little bit of computational technique. So I am not mainly a computationalist, but I am mainly an experimentalist. But yeah, I do some molecular dynamic simulations also. Here in Germany, I also did some terahertz spectroscopy. I learned the terahertz spectroscopy, and I also learned some nonlinear technique of the terahertz spectroscopy. So what do we mean by nonlinear? I will come later. And in UT Austin, at UT Austin, I learned the 2D IR, two-dimensional infrared spectroscopy of the spectroscopic technique. So actually, this terahertz is also lies in the far infrared region, and this 2D IR I used to do in the mid-infrared region. Okay, that's all. I would like to acknowledge all of my funding agencies like Desenpost Center. So during my, I completed my MSc degree as an integrated PhD fellow. So during MSc also they gave some scholarship, and then Inspired scholarship, DST, University of Calcutta. So my thesis was awarded by University of Calcutta. Then the result, this is the funding agency where I work in Germany, and actually I am affiliated to TU Dortmund. But since my boss was the main lab was in Ruhr University, Bochum, I stayed in the Ruhr University, Bochum, and after that the University of Texas at Austin. So without this funding, it's never possible. Also now, I would like to acknowledge GITAM. Funding is very important for research. Okay. Next, come to my research topic. So broadly, my research, my background is physics, but broadly my research is aligned a little bit of physics. I use very little of physics, very little bit of chemistry, although I don't know anything about chemistry, very little bit of biology, and little bit of mathematics. Okay, so my research category is little bit of interdisciplinary science. There are three, not three, but according to the 8-9 textbook, 8-9 class textbook, there are three states of matter: solid, liquid, and gas. Whatever, if you remember, whatever Dr. Das Mahanta has told, that she works on the solid state of the matter, like in the material property. What I want to investigate the liquid state of the matter, that is the in aqueous solution. So I used to have various molecule and put it in the water, mix it with the water, and investigate the property, what is happening to the solvation. Solvation means water around the molecule. Okay, because water in pure state and water in the confined state has very different property, and in various biology like liquid phase separation, protein denaturation, or protein stabilization, these hydrogen bond interactions or this water, the biological water, plays a very crucial role.
Debashish, what is called? Sorry.
Yeah.
No, continue.
So whenever you put some molecule into the aqueous medium, water, then some water molecule is always surrounded that molecule. That is called hydrogen bonded water, hydration water, or biological water. Because biologically it's very important.
No, I'm saying water H2O is already closed molecule.
Yeah, so that water around the molecule and the water in the pure state is completely different. They are showing different properties. And for every biomolecule like protein, to remain active, to remain its efficiency, to show its efficiency, that biological water is very important. That's why it's called biological water.
So is it the water you are studying or the molecule?
Yes, the water I am studying.
So water confined between two molecules. Can I assume
Yeah,
it like
so
that?
not like single water. Many water
No,
confined
it's a
between
group of water molecules confined between two.
around the molecule. Confined around the molecule.
So
And
I
in
think you mean they group of water molecule confining another molecule.
Yes, like this.
Yeah, so
This
they
is
are
a cation,
confining.
This
Yeah.
is anion, but a lot
Yeah.
of water molecule around it.
Yeah, so they are
connected
confining
with
something.
electrostatic interactions.
Yeah, that
Okay.
is the electrostatic
Yeah.
interaction.
But for this case, let's say for this protein,
Uh.
there is no electrostatic interaction, but there are hydrophobic interaction or hydrophilic interaction.
Is there also hydrophobic interaction?
Yes, I will come to the hydrophobic. What is
Where is
hydrophobic?
electrostatic interaction coming?
Yeah, so in water, H2O, that O has some delta negative and 2H has H plus, delta plus. So one oxygen has little bit of delta negative.
Mm.
Not single electron side, but slightly negative charge. So negative charge clouds is actually towards the oxygen.
So actually polarized. Little
Polarized,
bit polarized.
yes. Water is highly
polarized. And your molecule is also polarized.
Molecule is also polarized sometimes. For this case, it's cation anion, so they have electric charge. For this case, there is no charge there, so their hydrophobic interaction plays the role.
So sort of dipoles, right?
Sort of dipole. So
And
I
dipoles are
actually
hanging around
in the medium. So actually, terahertz spectroscopy can probe the dipole interactions.
Mm.
Okay. Okay, I have planned my talk like this way. I will discuss a little bit about hydrophilic interaction, that is the electrostatic interaction, putting some salt molecule into the water. Then some hydrophobic interaction. There is no charge here, only hydrophobic. What is hydrophilic? Hydro means water and phobic means phobia. There is a fear of things. So hydrophilics always loves to water, and hydrophobics, they don't want to interact with water. That's the main function. And then I used to have some combination of both of things. Like I have some molecule which has combination of charge and also hydrophobic thing. Okay. And finally, I will also discuss slightly more on the cryopreservation things, but very little. Okay. Let us go. So first of all, what are the experimental technique that I have used? The main technique that I have used that is the vibrational stretching or vibrational modes or stretching modes. To probe those modes, I used to use this FTIR machine. So this is the very important and crucial instrument for me. Let us move on. So I used to study the size of the protein by the dynamic light scattering method, DLS spectroscopic technique. This is a very common method. I use the circular dichroism method 3D to measure the protein structure and to measure the hydration, that is the very localized hydration with the fluorescence spectroscopy, but time dissolved fluorescence spectroscopy. And also I have used a global collective hydrogen bond dynamics with terahertz time domain spectroscopy. So I specifically mentioned these can measure the localized hydrogen bond interaction, but these can measure the all dipole-dipole interactions in the whole medium. So that's why it's a
What is mean by localized and global?
localized means very close to the molecule.
Oh,
So
so what is that like dimension like?
yeah, for the fluorescent molecule, you need to have some fluorescent probe mixed with the system.
Correct.
Because the molecule which can emit light, that only we can measure. So it can give you information around the probe molecule, not not my interested molecule or not the water molecule, but around the probe molecule.
What
But
is the
for
probe molecule?
I have to mix some probe molecule to get the signal from the fluorescence spectroscopy, because it's a fluorescence spectroscopy. It can measure only the emitted light. What is the light it is taking, going up, absorbing and going to the upper state, then whenever it is relaxing back, some light is emitting. That emitted
So
light
basically it's a molecular spectroscopy.
is a molecular spectroscopy, both. But this one is the absorption spectroscopy, not a emission spectroscopy. Terrestrial spectroscopy, there is no need of probe. The water dipole we can measure, but not a single. Every time I am saying this is always active to the collective hydrogen bond dynamics. It can probe to the collective, not a single one. Okay. I also have used some other techniques like optical pump, optical probe spectroscopy. This is a time dissolved spectroscopy. That is also a time dissolved spectroscopy. But here I have used pump probe method with optical and optical. That means a 800 nanometer light which we can see. It's a red light. So I pump with the 800 nanometer light, and I also probe with the same light after some time delay maybe. So here what is the information that we want to get? I have a chopper here. What is the role of the chopper? Chopper can chop, that means can block one cycle. Let's say this is a laser light with a pulse laser. So it will emit one pulse, then after certain time it will emit second pulse, like that. And that chopper will chop, let's say, one cycle. So after each two light, it will chop one light. So I will get information once the pump light is present and once the pump light is not present.
That's a mechanical chopper.
That's the mechanical chopper. Yes.
This is a mechanical.
Mechanical.
What
Mechanical,
exactly?
electrical. I mean,
So that is the delay, right?
that is the delay.
Delay.
Delay is
you are already
the
producing.
not delay. Sorry, delay is here. This can move, going up and forward and backward.
What is the path difference?
Path
Path
difference.
difference.
So this will give you some delay in the time also.
That's a nanosecond, right? How much? Picosecond.
Picosecond.
That's a
Nanosecond is
picosecond.
fluorescence.
Nanosecond is like too much.
Too much.
Large distance.
Yeah.
So, what does it mean? Like here, you mean by chopper
Yes.
of the light?
So chopper just thing like that. It will do like this. So
there is no,
one time it will chop. I cannot see you. Then again I can see you.
there is no photon splitting happening here.
Huh?
There is no photon being splitting. nothing.
Not
You
photon
are
splitting.
exciting
Okay.
after a
cannot
certain
split
amount
up
of time.
Beam is like beam is
Okay.
stopped.
Beam
and-
Beam is stopped.
Okay, that's it.
But the thing, the main important thing, beam is not a continuous beam.
Okay.
It is giving one pulse after certain millisecond time. It is a millisecond laser. Then after 1 millisecond maybe it will give you one more pulse.
So why you need that chopper?
Yeah, to get information with pump and without pump.
Without.
Because this will measure delta of absorption.
Correct.
So some light will absorb and go to the upper state. But you need to know what is the case in the equilibriated state.
So what's the frequency of that chopper?
This chopper is actually
as this
set with the laser light. So whatever may be the laser frequency, the pulse frequency, it will be exactly half of the laser.
Also, it allows some
That
time
is
to
two lights
reach
to
to that beam when
Two pulses are
two
coming,
pulses are cannot simultaneously. Also allow the some time of time delay between
No,
the two
no.
pulses.
No, there is already time.
This
delay.
laser
Ah,
is a, that's why I said this laser is a pulse laser.
Pulse laser.
It has 1 millisecond. So 1 millisecond light can travel a
Travel
long
a
distance.
long distance.
So you have some gap.
Gap.
At that time chopper can go.
Hmm.
So chopper will not cut two continuously light. Chopper will always cut one light.
One.
And one light it will cut. Like that it is actually sync with the laser. Synchronized.
So that is the pump pulse and that is the probe pulse.
This one goes here and comes pump it. And then it is just drop. Nothing else it is doing.
And that is the probe.
Okay? Now probe pulse coming here with after some delay.
Okay, so
It
you
is
are saying
coming.
that chopper is to make the difference between pump and probe. Is it
Chopper is just one pulse, it will cut. Nothing
But I
else.
mean, you can always control on the laser source.
Yes. Now to get to that point, so pump is coming. Let's say I fix this delay such that the probe is coming at the same time. So that is zero delay between the pump and probe. After that I put slightly behind. So there is a gap now. After 1 picosecond the probe is coming. After 2 picoseconds the probe. So I have the full dynamics. The molecule is going into the upper excited state, and then how it is decaying. The full picosecond time scale I have.
Infant design is here.
Yes, this is home build. In the assembly center, this is
Yeah.
home build.
We told that I will
G2
be
measurements are there.
Okay. Does
Exactly.
it not affect the wavelength of your laser?
No, because the wavelength is fixed, 800 nanometer.
No, because that chopper is
Yes.
kind of is a barrier.
This is
It
a
might
mechanical
create
chopper,
a
nothing to do with the
diffraction pattern or something.
No, because
Just block
that's-
and block.
same thing. The gap between the two pulses is very high. One pulse comes,
Uh-huh.
it
Can you
will
draw it? It will be easier for
It
me.
will
No,
not
because-
interact with the second pulse.
Anyone is having them?
No.
Because why did I ask this question is because if the barrier is very narrow, the wavelength
Yeah, I can understand what you are
Yes.
saying. Like one pulse come, after some time one pulse come. Now, if the time between the chopper can cut here and here also, then the diffraction interference can work.
Okay.
Come into the picture.
Okay.
But the chopper frequency is such that it will only block this one. There is no interaction with this second pulse.
Okay.
But
There
the
is
back
no
pulse.
interference between the
No
two
interference
pulses,
between the
two
pulses.
So
Is it simple background subtraction you are doing using chopper?
So, no.
Not
Only
background.
I want to get information with pump and without pump. What is
Yeah,
happening?
that's what background.
Yeah, that's the background. Sure. I mean, without pump, it's a background. So without pump means that is in the equilibrated state. Nothing come and part of my system. Now pump work is to part of the system. After that, I am measuring actually with a probe. So it's just like that. I am the Debasish, but somebody came and एक थप्पड़ मारा जोर से उसके बाद बोला कि how are you feeling? That's pumping, and then I am measuring that how I am feeling. GITAM always do
So
it.
what's the tolerance of
What's the tolerance of?
like relaxation dynamics? How quick it
Yes.
is? It's like what's the order?
Yeah, so that will depend how my the laser resolution is. So let's say and how my delay resolution is. Let's say you have delay resolution of 1 nanosecond. So that means you have information at 1 nanosecond. Then next is 2 nanosecond. So you don't know what is happening in between 1 and 2 nanosecond. But let's say you have some femtosecond resolution now. So you know what is happening at 1 femtosecond, 2 femtosecond, 3. So you can say the dynamical information in the femtosecond time scale.
So
But-
I need to know the system that which dynamics they are following, then we can accordingly like design that probe and pump, right?
The
Lifetime of the system.
Generally, it's in
Actually, on the opposite. People measure what is the lifetime of the molecule. It is on the
Of
opposite.
course, it
Opposite,
depends on
But
the
you can get one estimate by using this potential surface, how the energies are.
Yes. Yeah. Okay, let us go back. Go. So here, this and this differences here, I use the same optically pump with 400 nanometer, but I probe with a terahertz pulse now. But the problem with the terahertz or IR pulse, you cannot see it now. So this blue lines is actually nothing. I mean, you cannot see this pulse. So that's a very high challenge to work with the terahertz pulse. That is also a home build setup, but I should not say that I build it alone. I build it with many others also. This is very complicated. Because here we have 3 pulses, not a single one pulses. To create a terahertz, we need a optical pulse. That's the challenge here.
So a lot of bulk
Okay.
optics is required, here, right?
Lot of bulk of optics is
Yeah.
required. Yeah.
Baby splitter and those
What is the expensive here?
What is expensive here? So these all components are optical components. Third labs.
Third
Like either your mirror or a beam splitter or this one is the BBO crystal. This is a nonlinear crystal. Very costly. This is also GPA, gallium arsenide phosphate. This is also a nonlinear crystal.
Semiconductor.
Yeah, semiconducting. So whoever can show a nonlinearity, you can use it.
Those are the major costs.
Yeah. So why we are using gallium phosphate? To combine this 800 nanometer with the terahertz light. So nonlinear crystal can combine or can divide also. So sometimes people also use here this same nonlinear crystal to create terahertz pulse.
The biggest was a Tie-Sapphire laser. This is very costly.
Tie-Sapphire laser is
Rest
amplified
can be
laser
handled
system.
within $1,000.
Yes, amplified laser system costs more than 1 lakh. More than 1 lakh or now, many lakh. Okay, this is how to detect. Why? What we are saying that how to detect a terahertz pulse. Should we elaborate this one? Then move on.
नहीं करो.
Okay, good, okay. Okay, let's come to the here first. Here I have used a gallium arsenide phosphide. Okay, forget about the name. This is a nonlinear crystal which can merge two light, one optical and one terahertz. Now comes here. Let's say first you don't have this terahertz pulse. There is an optical pulse. This optical pulse is coming from your tri-sci laser system. So this is highly polarized. So you will have a polarized light. Whenever this will pass to the electro-optical crystal, nothing will happen because it's a single polarized, and there is no other light to interact with this one. Okay. Then I have used a lambda by 4 field. Lambda by 4 field can give you a lambda by 4 or pi by 2 phase difference. So this will become a circularly polarized light.
Correct.
Now I use a Wollaston prism. Wollaston prism can divide into a 2 factor of that light. So everybody knows that if it is a circular, then you have the x square and y square. Just it divide into ix and iy component. Okay, and here I measure the difference between ix and iy. So when there is no other light, when it's a perfectly polarized, then I will get 0 here because both are same intensity. Ix and iy are both same. Now I use a terahertz pulse comes into the picture because I want to detect the terahertz pulse. So this is like a background. Background, everything is 0. When this terahertz pulse comes, this will interact with the optical pulse. Now this optical pulse is very small. You can question me that how this will interact with this one. So this comes because the group velocity of the terahertz pulse will interact with the phase velocity of the optical pulse. In other means, I can say this very small phases are there.
So
in
it's a
between the
amplitude and frequency modulation.
amplitude and frequency modulus at the same time. So then the polarization will be changed of the optical pulse. So I am always measuring the optical pulse, not the terahertz pulse. So the phase will be changed. So now my polarization will be changed to any other polarization. Let's say elliptical polarization. Elliptical polarization, when you here it says circular. If it is elliptical also, after crossing the lambda by 4 plate, it will be elliptical. After Wollaston prism, now my x and y component will be different. There will be certain delta. Now if I measure the gap, the subtract the ix and iy component, I will have some delta.
So you are measuring the ix and iy separately.
Separately.
How?
Two photodiode is here. The intensity, I is intensity. But that intensity is modulated by the phase also,
That is
amplitude and phase also. So it is actually having the information of the terahertz pulse, how your optical pulse is changing. So it is indirectly you are measuring terahertz.
So that photodetector is measuring the terahertz signal.
No terahertz, nothing we are measuring terahertz. We are all time measuring the optical pulse.
Acha.
Photodiode is
Terahertz pulse is a probe actually.
terahertz pulse only induces the optical pulse, nothing else. Because this photodiode will not.
That is a standard photodiode.
Photodiode will not work on the terahertz range.
Yeah,
This will only work for 800 to 400. This is optical range.
I mean standard.
The phase information of the terahertz pulse is only going through the optical pulse.
So this setting is completely for probe.
This setting is only here. This is my nonlinear crystal. Then this is the lambda by 4 plate. Then this is the Wollaston prism. This is the two photodiode. Only with the detection line. Okay, I mean if I explain each and every component will take that much of time. Each and every, I mean generation also. Generation is also very nice. In this generation, there are 3 methods of generating the terahertz pulse. Whatever I have shown here, I have used a semiconductor, 2 semiconductor. Laser light is coming and then semiconductor hole pair are generating. This laser light is falling here and hole and electron pairs are generating. Now how these electrons and holes pairs are moving, with that information you are actually generating the terahertz pulse. Because electron holes are moving, that means there is some current. And whenever there is charged particle moving, it will give some electric field. And that is my terahertz field. But this is the with that method. But in that method, I have used a BBO crystal to make the 800 nanometer to 400 nanometer. So I have now 800 and 400. Then I tightly focus it in ER. It will create an ER plasma, and from the ER plasma it will create terahertz pulses. So there are 3 ways actually to generate the terahertz pulse. The third way is just use this nonlinear crystal here. It will pass through the nonlinear crystal and give you the terahertz pulse.
So this setup is in
That's cheap and easy way.
Easy way, not cheap, easy.
Not cheap.
Very easy. Controlling is very easy, but here controlling is very difficult.
So is it available in SMOS?
SN
Like
goes,
if you want to
this
contain-
one is not available. This one is in Germany,
Uh-huh.
RUB, and this one is available in
So if you want to do this measurement, you have to send your sample or go to Germany.
yes.
Or
But
you
I
have
can,
anyone can do
but I
it.
can measure the steady state terahertz with the FTIR instrument.
That we have here.
That we don't have here, but
Any modification
you
on
can
that
buy
can
it.
do it?
So what do you want to do here?
Because it to Germany sector, we don't also have this ecosystem.
In essence,
We
yes.
also use this pump and flow method.
Where?
So in India, no one is
ISC
doing
also don't have. Only Aizer Pune, sorry,
Pune is possible.
Aizer Pune, Pankaj Mondal. Professor Pankaj Mondal have this thing. So he is still building. I don't know it's working or not, but he is having it.
You know?
I don't know personally. I just meet in conferences, and that time I was a student.
So why is it very one?
Okay, so what is actually terahertz? Terahertz is 1 terahertz correspond to 10 to the power 12 hertz, and its time scale is 1 picosecond inverse, and the energy is 4 milli electron volt. This is very important numbers. 1 milli electron volt, very less energy. That means you can measure biological sample. It will not hamper your sample. It will not destroy your sample. It has a time scale of 1 picosecond inverse. That means in the system, whatever is happening in the picosecond time scale, you can measure it. Like hydrogen bond breaking making happening in the picosecond, sub-picosecond time scale. You can measure with the terahertz scale. It has nothing else so important. Only thing is the energy is very less and time scale is picosecond. And it falls between microwave and infrared region. That's why I call it far infrared. So microwave can rotate the molecule. Whenever there is a rotational motion of the molecule, microwave can measure it. And this vibrational mode, this infrared can measure the stretching frequency of a pure bond like OH. H2 has a 2 OH bond. It can measure the OH. But this energy is very small, little, so that it can measure only the intermolecular interaction, not the OH. Because it don't have enough energy. The energy is resonating with only the intermolecular interaction, either van der Waals interaction, either hydrogen bond interaction, or anything, but very low energetic modes. It will
So
measure.
temperature is also below the room temperature, right? So room temperature is 25 millielectron.
Nothing will happen to the room temperature also.
So it is below the room
No,
temperature.
no, you can measure at 100 degrees Celsius also. Because the pump and there is a probe, you are measuring always delta A. I mean, always there is a background effect cancellation, noise cancellation effect is there. So anything is part of by you, that only you can measure. Local. Got it? Okay, this is a typical example of a water modes. This is a hydrogen mode stretch mode. If two molecules are stretching or compressing, this is a librational mode. That means one molecule is hydrogen bond, another bond is open. So this is called librational.
This symmetrical stretching or like two
Yeah.
bonds?
So here you have both symmetric and asymmetric also. But in hydrogen bond stretching, symmetric, asymmetric, you cannot distinguish it. Very small, weak energetic, na? So you cannot distinguish.
So in the first slide, actually, you are showing some pictures of that hydrogen and oxygen.
Ah.
So some bonds are clear, right?
Yeah.
But some bonds are in the form of cloud.
Defect. Yeah. So I am coming to that picture again. I maybe I missed your slide. Okay. I also use little bit of computation facility also. So I only use classical molecular dynamic simulation. No quantum. I don't know any quantum computation. Only classical molecular dynamic simulation. So in the molecular dynamic simulations, I have some system with let's say 1000 molecule or 2000 molecule. Now, with each and every molecule, if there is some interaction, intermolecular interactions, I calculate with a geometrical criteria. That means if the distance between two water and the angle between this one, OOH, is less than a cutoff distance, that means those two molecules are bonded. That is how hydrogen bonded is defined. Okay, that's the definition of hydrogen bond. Now, due to this, from this definition of hydrogen bond, you can have the information of the whole network, collective network. Either all the molecules are hydrogen bonded, or either not, whatever is doing on the molecule. Now, you can map this problem to mathematics also. What is my aim to use the spectral graph analysis? Maybe they can describe little more about that. But the main idea is that I have total 1000 molecule, so I can create a 1000 cross 1000 matrix. With every AIG, if they are connected, it is 1. If they are not hydrogen bonded, that is not connected, it will give you 0. So it will be a real matrix with 0 and 1 number and symmetric. Symmetric means if IJ is connected, JI is also connected.
What do you mean connected means?
Connected, that the definition I said, I use geometrical criteria. If the distance between two water molecules is less than a cutoff, an angle between oxygen O is less than a cutoff, then two molecules are connected. That means there is a hydrogen bond exists in between these two molecules. That means the Aij component is 1, otherwise 0. Though I can form a n cross n matrix, n is the system size, number of molecules, and I can calculate various parameters from the matrix.
That information to them, what fruitful things they will get from there. What they
Yeah,
will
so
get
it's
from
a real symmetric matrix, so it
So you
can,
need to do some operation on that matrix.
yes, and it can give you that how the path is going, like what is the minimum steps with which you can cover the whole system, because there's a connector, na? So with each step you are going from iron molecule to joint molecule if it is connected. From J it cannot go to K because it's not connected. From J it can go to L.
Is it a random mode model?
It's a, maybe we have to use
It's a
it.
complete
We need
like
to model
a
it.
networking kind
Yeah.
of thing.
So I'm not very sure about this thing, but yeah.
So you're trying to optimize the
Optimize,
geometries of the
No, geometry is already optimized. Once you create the molecular dynamic system, geometry is already optimized. Okay, what I did in my PhD time, I used to study this hydrogen bond breaking and making event with hydrogen bond jump mechanism. What is hydrogen bond jump mechanism? It's very interesting. So this is, I call it partner exchange event. Let's say first molecule was hydrogen bonded to this one, previous first. This is the initial, and there is no final bond at that time. Let's say like that. After some time, the final molecule from very long distance come closer to the zeroth molecule, and then this oxygen, this water actually rotate with a large angle and form hydrogen bond with this one. And finally, this is the hydrogen bond. Actually, there is no hydrogen bond here. So it actually changes its partner from one water to another water.
What governs it?
Now what is the difference between previously people think that it is a diffusional dynamics. Diffusion means very small angle. Very small angle, all this hydrogen bond can rotate with a very small angle, less than 10 degree. But what people have found that this can rotate with more than 90 degree also. So this is called large angular jump mechanism. And what governing actually this rotation, I mean what actually provoking the water molecule to rotate, I don't know.
The trigger for all this.
The energy fluctuation maybe.
Yeah, Debasish.
Yes.
Here, how do you keep track of these molecules? Means
Yes.
who is who?
Who is who? Yes.
Yeah,
Very
means
good question.
you might mix
so
up-
once I prepare the system from the molecular dynamics
Yeah.
simulation, I say I have a box with 1000 molecules.
Yes.
So I have the information of each and every 1000
Are
molecule
they
into
indexed?
3.
Are they
atom.
indexed by? Are they indexed by some name?
Let me finish.
Yeah.
So I have each and every atom information,
Uh-huh.
the x, y, z coordinate. So let's say molecule number 1,
Okay.
x, y, z coordinate of H, x, y, z coordinate of H2, x, y, z coordinate of O. I have full information of the 1000 molecule.
Okay, so so then you know the trajectory or something.
Trajectory. I know
Okay.
time dependent coordinates.
So in practical, so I think this is simulation.
This is
So in
simulation.
practical,
In practical, you cannot.
if, maybe using heavy water or something, could it be?
In simulation, we can do it. Just replacing this one by deuterium.
Yeah. You know, in practical.
In practical, we can change the H2O to D2O, but we cannot keep track of each and every molecule.
Okay.
This is impossible.
Distinguishability.
Nahin.
There is
All the
no
water molecules are
There is
same.
distinction.
But in the simulation computer, you can track. Yes, ma'am.
So I was just wondering, these kind of simulations, what are the kind of parameters that you have to plug in?
Yeah. So I only use till now classical molecular dynamics simulation. So I use force field. So I am not a force field builder. Whatever the force field are there, I use GROMAX software. So in there, I basically use CHARM 36 force field many times, OPLS force field many times. I don't know much about the force field. This is
Basically the interaction, so it's how.
it's a Lennard-Jones potential.
Okay.
Lennard-Jones.
It's really very, it's like a quantum mechanical calculation has
Yes.
been done for a long time to really
Long
get
time.
these force fields.
It's established.
It's like he's saying classical things, but I think inside there is some quantum mechanics is already hiding in the force field.
Yeah.
Do you also take count of molecular orbitals of oxygens?
No, then you have to go to quantum. Molecular orbital cannot do with the molecular
How do you
classical.
decide orientations?
Classically
It's
can.
like more like geometry.
But everything is optimized. It's not like vague thing. Like the whenever you are doing the optimization, that is done by, as Vijay said, that is done by quantum mechanically. But finally, whatever you have the final information, the quantum information actually lost. So you don't know the molecular orbital. You don't know the energy states of the molecule.
He already have the expression for the energy where it takes a translation, rotation and many things. each term contribute to the
From the force field.
Final thing is going to govern by the interactions of the molecular orbitals. Right?
Yeah, and mainly
How will you
That is
go to
included in the force field.
maybe Harita can also comment. She is also working on the same.
Yeah, basically the force field you only have these electrostatic interactions.
Yes.
Basically, there is no quantum in the picture. Totally works on Newtonian mechanics. But whichever the bond angles, bond length, all those things are coming from geometry optimization and quantum mechanical calculation. That parameters are from that, but how the things work out is basically Newtonian mechanics.
Actually, like last time, Harita also described how she works on DNA and other things by using computers.
That's why we were not there.
Okay, let me go. Now, hydrophilic interaction for the time being. I am skipping the hydrophilic one. It's not so interesting. Time will not permit. I am going to hydrophobic one. Hydrophilic one is not so interesting. Whatever I have found the final idea, like you have some water molecule connected in pure water. There is nothing perturbating. So water molecules are connected through hydrogen bond. Whenever you put some salt molecule, that means cation. One plus charge, one minus charge maybe. If the plus charge is smaller one, that means I use single charge, but smaller and then larger. That means density is very high for smaller, density is little less for the bigger. So this high density molecule will just attract the water molecule and hold strongly to the molecule. So those molecules will not be a part of the water network. But here that molecule can create a full big collective hydrogen bond network. That's what we found. And we also did with some protein molecule, and we found that there is no interaction with salt and protein, at least for this protein, BSA, bovine serum albumin.
So here, what kind of interaction is taking place?
Electrostatic, completely electrostatic.
Hydrophilic.
Hydrophilic means that want to interact with water. Since there is a charge here and charge here, so it wants to interact. Those are hydrophilic. Now comes to hydrophobic interaction. So here I have used this molecule. Forget about the chemistry of the molecule. So it has some 2 oxygen. That 2 oxygens can form hydrogen bond between water, with water, not between, with water. So if you decrease one carbon, this molecule becomes this molecule. If you increase one carbon in between, this molecule becomes this one. So this one are carbon. This is 1 carbon, 2 carbon. Here only 1 carbon, and here you have 3 carbon. Both are practically insoluble in water, but this one has an infinite solubility in water. From pure water to pure DME, you can solve it. Mix it. Okay, that's why I picked this molecule during my PhD time. I have used so many ND simulations and also terahertz spectroscopy with this molecule only. Okay, so here what I found, I have taken the OH vector of the water. I can easily calculate the OH vector. Vector is just what? R1 minus R2. Then it will be directed from R1 to R2. So then there is a direction. That direction I take the angle between my Z axis and the OH angle, and I plot that angle cos theta value here. I can directly plot the theta value also, but it will just mapping from minus 80 to plus 80 to minus 1 to plus 1. I just took cos theta. Whatever I found that there is a small diffusional motion, so theta is little bit changing. But suddenly there is a big jump, almost from minus 180 to plus 180. So these are the signature of hydrogen bond jump mechanism. So in the system with the diffusion motion, there are some jump mechanism also happening.
So this happens here as well, right?
This happens here as well, here as well, like this. If you can remember Sankaran's talk, Sankaran did similar kind of thing with polymer, but completely analytical thing. What he found that there are some dynamical heterogeneity, but I found also the same thing, dynamical heterogeneity. So let us explain this picture first. This is the number of jump molecule divided by average number of jump molecule. So let's say all the molecules in my system, simulation, completely simulation.
Full slide.
Yes. Let's say all of my molecule is moving with the average diffusion coefficient. Then n by ng will be 1, and I will get a completely homogeneous structure. Okay. So if all the molecules is same, then I will get only a single line. So if they are homogeneously distributed, then I will get at 1 there is a peak. But whenever I go to 500 femtosecond, very small time gap, I found there is a maxima at 0. So that means the molecules are very, kind of restricted. They don't have any motion, dynamical motion. Localized kind of, their diffusion motion is very, very restricted. Now if I increase the time scale, the thing peak at 1. I change the concentration of the water, I found the same thing in all the cases. So this is called dynamical heterogeneity or temporal heterogeneity. This is not structural heterogeneity, because you change the time scale and you are getting the heterogeneity. Now I want to investigate why this is happening. So the one answer is with the diffusion motion there are some this large angular jump motion is also there. This is one reason, and the second reason is that in the system there are some structural heterogeneity also, which forces the water molecule to restrict. It cannot move. So in the same system, this is also an empty simulation picture, whole slide. In the same system, I calculate and found that there are some closed homostructure where the same water molecule is connected to the two atoms of the same molecule, DME molecule. A single water molecule is connected to two DME molecules at the same time, and a single water molecule connected here and one bond is open. So that means these are actually restriction applying on the water molecule, different kind of restriction. That's why this heterogeneity comes into the picture.
So Debasish, the structural heterogeneity and dynamic heterogeneity, the time scale is different or?
Dynamical heterogeneity is the heterogeneity in the time scale, but structural heterogeneity there is no time scale, only in the hydrogen bond structures.
Because when you perform MD calculation, did you clear on the time scale?
Yes. So my system resolution was 5 femtosecond, and this is happening in picosecond order. Hydrogen bond breaking happening in picosecond order. So my resolution is enough. And then I also find there are so many water molecules in the system, but only this 10 to 20 molecule is connected here. So these are called water clusters. This is called water cluster. So many water clusters is actually confined in the system. Okay, so this one is we understand that there are some heterogeneity in dynamic, there is some heterogeneity in structural also. Let us go to the next topic. This is I like this topic very much because here I use alcohol molecule, and alcohol is my favorite molecule. Why not? So alcohol gives shows very non-monotonic.
Keep it restricted.
Yeah, alcohol shows very non-monotonic dynamics. So it's not like a monotonically it is increasing or monotonically it is decreasing. It will increase sometime and it will decrease sometime. Like in which parameter? This is comes to this slide directly. This is there is some protein molecule here and there is some water alcohol molecule here. I fix the alcohol concentration as 5% in the whole system, and I vary the protein concentration. Okay? I measure the terahertz absorption coefficient. Whatever I found, first absorption decreasing because I am adding the protein molecule. So that means I am replacing some water molecule and adding the protein molecule. Protein is hydrophobic, protein is not polar, water was polar, so that means that alpha decreases. Because absorption coefficient is linearly proportional to the dipole of the total dipole of the system. After that it is suddenly increasing. Now what is happening? Since these molecules, alcohol molecules are hydrophobic, they have some carbon. They don't want to interact with water. Now they got their friend. This protein molecule is also hydrophobic. Due to the preferential hydrophobic interaction, they come closer together and go to the core. Because whenever you put the protein into the water, the outer part will be hydrophilic, inner part will be hydrophobic. Because outer part it will interact with water, but inner part it will not interact with water. Whenever the alcohol molecule goes into the core, this protein has to open up. So that's why now my total volume increasing. My solvation area is also increasing, biological area is also increasing. That's why there is a sharp increase in the thing. So this is actually not very common in all.
Protein has to open.
Protein has to open.
What does it mean?
Protein has to open means the stability, the structural stability is not there. So there is some kind of denaturation happening on the protein.
So there will be a lot of fragment bond will be there, like
You can say like there a lot of inter-protein connection is loose.
So, Debasish, how about the dangling bonds here?
Dangling bond of water.
Hmm?
There should be some dangling bond because whenever there are some hydrophobic moiety, so the water molecule don't find their partner, so it will dangle. It will not
So
making hydrogen.
that information do you get from here? Any of the measurements?
From the MIR, mid infrared, you can get it. There is a certain area where the dangling bond comes.
Okay, they have the signature. Also.
Signature, yes.
Okay.
They have the signature. So this work is actually highlighted in the Chemistry journal also. Okay, conclusion I already said with this same picture, this picture. Whenever the protein is put in the water, it will make a globular structure. But whenever the alcohol molecule comes to the core, it has to open up.
Actually,
So-
surface energy actually reduces by this, by
Surface
addition.
energy increases.
I think it should depend on protein as well.
Like protein.
It should depend on protein as well, but it's a very general picture. I used three
In most of
protein.
the protein it works.
Yes,
This is what you're saying.
most of the protein.
Okay.
But this happen only with alcohol. I don't know why. Not with
No,
other
actually,
substances.
I
Like
think
increasing
that,
and then again decreasing. It's
Ah.
Getting
non
some energetic is
Exactly, that is
obviously
your point.
Maybe
Decreasing
reject
or
it.
decreasing metal. You
Okay.
can calculate the energetics by the way.
Huh?
Did you try some GPCR protein? There is
No.
a set of protein which our cells can build up.
Mm.
Okay. So whatever my boss can buy the protein, I work with that protein. During
Now you are
period.
the boss, right?
I don't have money now.
We get no, that told.
Oh, sir, first FTI machine, I need it, sir.
Sir,
Really, you give me a FTI machine, I am guarantee you with 5 years I will produce 5 people. I am guaranteeing you. But give me a FTI spectroscopy.
5 के बाद दे रहा है तुम।
कुछ नहीं sir.
दे दी।
बाला
Okay. Now, now come to the combined picture. Now I took some molecule which have some hydrophobicity and which have some electrostatic effect also. Okay, some charges, some hydrophobicity. These are the molecules which have some carbon and which has some chlorine minus and plus charges. Okay, and whoever is winning the protein stability, that's the question. The question, finally going to the answer again. The answer what I found, yes, what I found, there are spectroscopy can distinctly different the two kind of interactions. One is the hydrophobic, this tetra, tri, all are hydrophobic. Look here, for this one, tetramethyl ammonium chloride, and this is the ammonium chloride. For ammonium chloride, the absorption coefficient increasing. That means it is showing hydrophilic effect. For tetramethyl, whoever has this tetra, tri, carbon, they are decreasing the absorption coefficient. That means it is showing hydrophobic effect. So terahertz spectroscopy can distinctly different the two types of molecule in the system. Whichever is showing hydrophobic interaction, whichever is showing hydrophilic interaction.
Do they
That is the
answer-
beauty
do
of.
they answer why or still we are? Do we know answer why this?
Yeah,
is
the
happening?
answer is that whenever you have some hydrophobic effect, there is not collective. The network is broken. The water network is broken. And terahertz spectroscopy measure only the collective hydrogen bond network. The system for which the network is bigger, you will get more absorption. So there is a lot of perturbation in the network. Very small network. Okay, scrap everything. Last final topic. So I want to continue this work. So here, whatever I found in the terahertz, this is a with normal FTIR spectroscopy I can do it. This is the hydrogen bond stretching mode, and this is the bound water mode. Whenever a molecule is bound with water, there is some signature mode in the terahertz spectroscopy. Whenever there is a molecule which is not connected to the molecule but surrounding the molecule, that I called a wrapping, hydrogen bond wrap. There is a signature of wrap also. Now, with this terahertz, these two signature, measuring these two signature and using some mathematical tool like principal component analysis, you can get the two main principal components and their scores also. From their scores, so whatever the system I am interested in is the cryopreservative system. What is the cryoprotectant molecule? When the temperature goes down below 0 degrees Celsius, water molecule freeze, it become ice. Then my protein molecule or the biomolecule cannot actually remain in this efficient state. It will lose its efficiency. So what people do to preserve the kidney, or maybe this is the picture of a brain, it will put some cryopreservative in the system, in the water, so that the water molecule cannot actually freeze. So it will decrease the freezing temperature of the water. Now what is actually happening on the hydrogen bond so that it's decreasing, and why not in the pure water? That's the question I want to ask. I want to check the same terahertz spectroscopy. This is the bound water mode. I calculate the slope and I got the bound water increases, and then after some time decreases. I check the same trend with the thermodynamic parameter. This is the delta H of mixing, and it shows a linear, I mean going with the same with the trend. That means that bound water is actually governing my delta H, enthalpy of the system, and entropy of the system is governing by the wrap water. But why not? So this is the system of glycerol water mixture. Glycerol is a very well-known cryopreservative. Next, I have used the DMSO water. See here, this is the wrap water mode. This is the bound water mode. Wrap water mode actually is directly correlated to the entropy of the system, mixing entropy, and bound water is directly connected to the mixing enthalpy of the system. So here you can say that all the thermodynamics is governed by this local hydrogen bond actually. So yeah, that's all. I also work in the liquid phase separation a little bit, not with the protein molecule, but again with the alcohol molecule. This is also
something for next talk.
Huh?
Leave something for next talk.
No, it's done. Thank you. Next time. Any questions? Feel free to ask.
so many.
Feel free to come to me anytime also. You have any questions.
Excellent, Debasish.
Okay, sir.
Thank you.
Thank you. I don't have enough
So
time.
I want to
Yeah, sure.
So in which field you can use this concept for commercialization?
Okay, this cryopreservation. My main goal is to calculate what is the efficient concentration in which cryopreservation works very good. So I have this one conclusion slide here where we found that 30% is the most efficient one. If you want to use DMS as a cryoprotection, then you have to follow this below 0.35. That means 35%. So that we found. So that is the thing one we need to understand with changing the cryopreservation, what is the most efficient concentration. And the second thing is what is the interactions mainly, why it is inhibiting the ice crystal formation like this.
I see DMSO and DME is very popular. I mean,
DME is not popular, DMSO is very popular.
Very popular.
Professor Biman Bagji in IISc Bangalore has a full live DMSO board.
Yeah. DME also used for this.
DME is not so popular.
DMFO.
DMFO.
Good picture.